Good morning, ma'am. I am Basil Dave Iradores, a reporter for today for the topic of synchronization hardware. Synchronization hardware typically refers to devices or components that are used to ensure that different parts of a system or network operate in coordination with each other. Synchronization hardware is like the conductor of an orchestra, making sure all the instruments or components play in harmony by coordinating their timing and actions. Locking in atomically. Locking is an essential concept in concurrent programming and is widely used to ensure that data integrity and consistency in multi-threaded or multiprocess environments. Locking is like giving each worker a key. Only the worker with a key lock can write on the document and others to await their turn. This ensures that the information stays organized and accurate, preventing mistakes that can happen when everyone tries to write at once. In programming, this concept of locking is used to keep things orderly and prevent data from getting mixed up in situations where multiple parts of a program are running simultaneously. Atomically, when synchronization operations are described as atomic, it means they are designed to be executed without interruption and provide a guarantee of indivisibility. Atomically is like a single, unbreakable action, ensuring that it completes entirely before anything else can interfere. This is important in preventing conflicts and maintaining order in situations where multiple things may be happening concurrently. Mutex locks. The simplest of these tools is the mutex lock. In fact, the term mutex is short for mutual exclusion. We use the mutex lock to protect critical regions and thus prevent race conditions. Mutex lock is like a key that ensures only one worker can access and modify shared information at a time. It prevents race conditions by creating a controlled environment, allowing each worker to take turns securely updating critical sections of code without interference from others. Disadvantage of mutex lock: deadlocks, lock connection, priority inversion, resource utilization, complexity and debugging, performance overhead. Deadlocks: lock can cause standstills if threads get stuck waiting for each other. Lock contention: multiple threads fighting for the same lock can slow down parallel processing. Priority inversion: high priority tasks waiting for low priority ones holding locks can lead to unexpected delays. Resource utilization: overusing locks can make threads spend more time waiting than doing useful work. Complexity and debugging: implementing locks can adds complexity and mistakes can be hard to find and fix. Performance overhead: using locks comes with some extra work and too many can slow down the program. What is spin lock? A spin lock is a synchronization primitive used in concurrent programming to protect shared resources from simultaneous access by multiple threads. A spin lock is like a waiting line for threads in program. Instead of waiting, threads repeatedly check if a shared resource is available. It's a simple way to ensure fair access to resources without wasting time in idle waiting. Semaphore. A semaphore S is an integer variable that apart from initialization. A semaphore is like a numeric flag in programming that helps control access to a shared resources. It's initialized with a certain value and is used by different parts of a program to coordinate and limit how many can access the resource simultaneously. Counting semaphore and binary semaphore. Counting semaphore can arrange over an unrestricted domain. Binary semaphore can range only between 0 and 1, thus binary semaphores behave similarly to mutex locks. A counting semaphore is like a versatile counter in programming, able to represent and control a range of conditions of resources for effective coordination. Binary semaphore is like a simple switch in programming that can be either on 1 or off or 0. Similarly to a mutex lock, controlling access to shared resource by allowing or blocking multiple threads. Deadlocks and starvation. Deadlocks can be prevented or resolved by breaking one or more of these conditions. Starvation is a concurrency-related problem where a process or a thread is unable to gain necessary resource or access to the CPU, preventing it from making progress. Deadlock situations where tasks are stuck can be avoided or fixed by breaking some of the conditions that lead to them. like tasks holding and waiting for resources indefinitely. And forced starvation is like a traffic jam in computing, where a task is stuck and unable to move forward because it can't get the resources or CPU time it needs. Priority inversion. It occurs only in systems with more than two priorities, so one solution is to have only two priorities. However, typically these systems solve the problem by implementing a priority inheritance protocol. Priority inversion is like a traffic jam where high priority task gets delayed because a lower priority task is using a shared resource. One solution is to simplify priorities to just two leads. Classic problems of synchronization. The bounded buffer problem, also known as a bounded queue or a bounded buffer queue, is a data structure that it stores a fixed number of elements. The bounded buffer problem is like a limited parking space for data, storing only a set number of elements, often referred to as a bounded queue or a buffer. The readers-writers problem is a classic synchronization and concurrency problem that illustrates the challenges of coordinating multiple threads or processes accessing shared data. Reader-to-writer locks. It allows multiple readers to access a shared resource concurrently while ensuring that only one writer can modify the resource at a time. The readers-writers problem is like managing a library where some threads want to read data, while others want to write. It highlights the difficulties of making sure everyone accesses the shared information correctly. The dining philosopher's problem is considered as a classic synchronization problem neither because of its practical importance nor because computer scientists dislike philosophers, but because it is an example of a large class of concurrency control problems. The dining philosopher's problem is like a puzzle in computer science, where philosophers must share resources, like forks, without causing conflicts, presenting a border challenge in managing concurrent processes. So that is all for my report, and thank you.